Today's problem is 9 divisors. Difficulty is medium. Given a positive integer n, you need to count the numbers less than or equal to n, having exactly 9 divisors. Okay. Example, if n is 100, the output should be 2. There are 2 numbers less than or equal to 100 that have 9 divisors. Those are 36 and 100 if n is 200. Output is 3. Now you have 36, you have 100, you have 196. Constraints. N is going to be somewhere between 1 and 10 to the 9th. What is 10 to the 9th? A billion. Topic tags. Yeah, binary search. I don't think we're doing a binary search. Prime number, sieve. Okay, yeah, here's the clue here. This is a weird time complexity. It happens to be the time complexity of the Eratosthenes sieve algorithm, which is an algorithm for finding prime numbers. So that's a tip-off. Now, there's something else that you need to know that probably most people don't know. I didn't know it. I had to look it up. And because of that, this is not the kind of question I would expect anyone to get in an interview. I mean, unless the interview is for some sort of mathematically intense job position. So I'm going to try a different pen this time. See if it works. 9 divisors. All right. So the first thing that I thought of was I'm just going to limit the search to perfect squares, okay? Because normally any number is going to have an even number of divisors because they come in pairs, except perfect squares, right? So, 36, for example. So the factors would be 1 and 36, 2 and 18, 3 and 12, 4 and 9, and then 6 and 6. But because it's a perfect square, the 6 only counts once. So it has an odd number of divisors. My attempt to do it with perfect squares timed out. So it turns out that any number that can be formed via this formula, p squared times q squared, p is not equal to q, and they're both prime numbers, that is going to have 9 divisors. All right. We're going to rearrange this a little bit to make it a little bit more usable. So, I mean, what we have here is p times q times q. We could rearrange that as p times q times p times q. And we could rearrange that as p, q squared. So now we can say that any number that can be formed as the square of the product of 2 prime numbers is going to have 9 divisors. On a related note, it turns out that any prime number raised to the 8th power also will have 9 divisors. All right? So, given that information, let's see if we can implement a solution. We can try the example with 100. I think I can still scroll this now. Yes, to new pen I can write and scroll. So let's use n equals 100 because we are supposed to get two numbers, 36 and 100. Let's see how that would work. I need some white space here. All right. Now I'm wondering what. Oh yeah, C is okay. So C is the count. Limit is the int value of the square root of n. N is 100, square root is 10. So limit is 10. We're going to have an array with limit plus 1, in other words, 11 elements. And we're going to fill all of the elements starting with 1 with their own, the element at 1 will be 1, the element at 2 will be 2, etc. So let's do that. We would have one empty spot at the beginning, and then we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. Now here's the sieve. All right, I is going to start at 2. Maybe I should keep track of. Should I keep track of I here? You know what? It's not really going to go very high. Let's just start with I equals 2. And we're going to run this loop until I squared is greater than or equal to 10. I is 2. If prime, that's the name of this array here. If prime at 2 equals 2, which it does, then we'll drop in here and say that j equals 2 squared. So j equals 4. And as long as j is less than or equal to 10, we're going to say if prime j equals j, if prime at 4 equals 4, which it does, then we're going to change prime j to I, which is 2. Right, so that is 2. And what we're doing here is storing the smallest prime factor of each number. All right, so we'll add 1 j will be, whoa. So j is 4, j is, we add I each time. I is 2, so that's going to go to 6. Is prime 6 equal to 6? Yes. Well, in that case, prime 6 is going to be 2. What's going to happen here is we're just going to go up by 2's, and we're going to change these even numbers so that the prime array shows their smallest prime factor as 2. All right, once we get through that, we'll go back to the outer loop. I is now going to be 3. So we'll say if prime 3 equals 3, that's right here, and it does. So j will be 9. So let's see, prime I is I, yes. So then int j will equal 3 times 3, which is 9. If prime at 9 equals 9, which it does, then we're going to change it to be I. So instead of 9, it's going to be 3. Now, when we increment, you know what? That's not even visible there. I just realized that the increment on the loop. Okay, so yeah, each time through here. So j equals 3 times 3 is 9. Is that less than 10? Yes, but after we go through once and we add 3 again, it's not less anymore. So we drop out, we go back here, I is now 4. 4 times 4 is not less than 10. So we're done here. We've got this prime array where for each index, it contains the smallest prime factor. Okay. Now let me see if I can scroll this up a little bit so we can see the rest of. Yeah. Okay. So now we've got the prime array. That's the Eratosthenes sieve. Now we're going to go through here, and actually I should keep track of I. Well, let me see. I can keep track of I. I could keep track of P. Keep track of Q. Not sure if all that's going to be necessary. Oh, I should keep track of the count also, because that's what we're returning. Count is initialized to 0. All right, so I is going to start out at 2. And it's going to run up to 10. So we're going to say int p equals prime at 2. What is prime at 2? Prime at 2 is 2. Okay. Q equals prime at 2 divided by prime at 2. Well, 2 divided by prime at 2 is 1. Okay. Now we're going to check for a p squared times q squared form. Now 1 is not a prime number. So if q equals 1, this doesn't work. So we'll just drop down and check for p to the 8th power. What is p? 2. 2 to the 8th is 256. That's too high. It's greater than 100. So we can't use that. All right. I will now go to 3. All right. P equals prime at 3, which is 3. And Q equals the prime of 3 divided by prime at 3, which again is 1. So that is not going to work. Again, if Q equals 1, that's not a prime number. And 3 to the 8th, really none of these numbers to the 8th, they're all going to be too big. So I will go to 4. Right. Let's see. P equals prime at 4, which is 2. Q will equal prime at 4 divided by 2, which is 2. Okay. This is not going to work because it's going to violate the P not equal to Q constraint. P and Q cannot be the same prime number, so that doesn't work. We're going to 5. P equals prime at 5, which is 5. Okay. Q equals prime of 5 divided by 5. Prime 1. Okay, so this is another one where Q equals 1, and it isn't going to work. I guess we can put that there. Well, you know what? Let's just see if we can just erase it. Does that work? I thought it would, but maybe. Oh, here it is. Oh, I'm sorry. That's the eraser. Erase. All right. So yeah, Q is 1 again. Right. I is going to 6. Let's see what happens. P equals prime at 6. Prime at 6 is 2. Q equals prime at 6 divided by 2, which is 3. All right, 3. So Q now equals 3. Check this. Is P times Q equal to I? 2 times 3 equals 6. Yes. Is Q equal to 1? No. Is P equal to Q? No. Well, in that case, we found a number with 9 divisors. and that is 6 squared, which is 36. All right. To save a little time here, I mean, you probably get the idea of how this is going. 7, 8, and 9 are not going to give us anything useful, but when we get to I equals 10, we would look for P equals prime at 10, which is 2. We'll look for prime at 10 divided by 2, which is 5. Prime at 5 is 5. All right. P times Q. Does P times Q equal I? 2 times 5 equals 10? Yes. Does Q equal 1? No. Does P equal Q? No. All right. So it gives us another count. That is going to be 10 squared equals 100. And then that's what we're going to return. So that's the algorithm. I think I can delete all the annotations in one shot here and change that, go back over here and run the algorithm. You'll probably see that I've tried and failed on this a few times because I was trying to make my perfect square theory work, and it didn't work. But anyway, this is the way to do it. I mean, if you have a better memory than I do, then you can maybe tuck that away. That any number that can be expressed as p squared plus q squared, where p and q are different prime numbers, or p to the 8th, where p is a prime number, that number will have 9 divisors. But that is the solution to the problem. Go ahead and like the video. Subscribe. You'll get problems of the day in your inbox every day. And we will see you next time.